All right, here we go. Last video for this chapter. We're going to learn about the connection between work and rotational kinetic energy. All right, basically, just one big example here that hits a lot of bases. All right, so I guess before we do anything, a couple quick things. So in the last couple videos, we learned how to calculate rotational kinetic energy, and we know that torque produces angular acceleration, which is going to change the rotational kinetic energy. But what's the connection? All right, well, it's basically the same as the connection between force changing kinetic energy and the work done by that force, okay? So when we talked about just linear values, here, let me begin this. Okay, so when we talked about work, we learned that for a constant force, the work done was equal to the force times displacement, okay? Well, we can use a jumper equation. We know our displacement is equal to change in theta times r. So there's our force times displacement. Just rearranging and regrouping gives us this, force times radius times delta theta. Well, force times radius is just torque times change in theta. So the equation is basically exactly what you would expect it to be, right? So for a constant force, we know that work is equal to force times displacement, right, along one axis. Right? And so the angular counterpart to this equation is, well, the angular counterpart to force is torque, and the angular counterpart to displacement is angular displacement. Okay. So what if the force isn't constant? Well, we learned that work is the integral of force with respect to the position. So similarly, work is the integral of torque with respect to angular position. Okay, so the jump from linear values to angular values is exactly what you would expect them to be, right? You just replace each of the linear values with their angular counterpart. All right, and the work kinetic energy theorem still holds. Our net work will still equal a change in kinetic energy, where this is change in kinetic energy plus change in rotational kinetic energy. Do I agree with that? I do agree with that, yes. Okay. So if you calculate the net work done on an object, you have found the change in kinetic energy plus the change in rotational kinetic energy? Yes. Okay, so finally, power. So we learned, I don't know, chapter 2 ago, that power was the rate at which work is done. You can find your average power by just doing work divided by time, and you can find instantaneous power by either taking a derivative or doing force times velocity. All right. In terms of angular motion, it's the exact same thing. Power is still the rate at which work is done. Force times velocity becomes torque times angular velocity. All right. And our equation for average power remains unchanged. I guess the big thing is usually when you're, do I want to say that? I don't think I do. Okay, so there we go. So, all right. I hesitated a little bit when I wrote this. So I know this is for sure certain if you've just got an object that's rotating. Next chapter, we're going to talk about objects that are rolling, where things get a little bit more complicated. And I need to sit down and do an example and see if this is still true for an object that's rolling. But for the purposes of this chapter, that will hold. Okay, and we'll definitely have to revisit that once we get to rolling. Okay, so basically, we're just going to dive into an example here. So let's begin this here. All right, so we've got this little system over here. We've got a pulley, and then mass 1 and mass 2. All right, so this is similar to what we did, the one we did yesterday, but this time instead of treating it from the standpoint of net force and net torque and looking at acceleration, we're going to treat it by looking at the kinetic energy, the gravitational potential energy, and the rotational kinetic energy. We're going to have to dig a little bit into forces in order for this to make sense, because there are a couple questions about tension. All right, so let's call this side, the tension on this side, tension 2, and we'll call the tension on this side tension 1. All right, so here's what we know. We know that mass 1 is 0.8 kilograms, and we know that mass 2 is 1.2 kilograms. We know that the mass of the pulley is 0.6 kilograms. And the problem tells us that it can be treated as a uniform disk. So I, for a uniform disk, remember, is 1/2 mr squared. And for us, the radius of the disk is given to be 5 centimeters. All right, so based on that, let's see if we can figure out what's going on. All right, so mass 2 is heavier, so mass 2 is going to go down, mass 1 is going to go up. That's going to cause the pulley to rotate this away. And it says if the system is released from rest, how fast will it, meaning the system, be moving after mass 2 has fallen 0.75 meters? All right. So what you need to notice is mass 2 is going to go down 0.75 meters. That means mass 1 is going to go up 0.75 meters. Okay. So there's a couple ways of doing this. Need something, Andrew? Okay. So we're going to approach this from conservation of energy. Okay. So I am unwisely going to abandon my my notes, and let's just do this. All right. So at the beginning, let's just call the height of each individual thing 0. So let's assume they don't have any GPE, because you can certainly lengthen this one string so that both masses are sort of at the same position, right? So our total energy initially is 0, right? All right. After we release it, what are we going to have? Well, mass 2 or mass 1 will have gone up, so mass 1 will now have some GPE. Mass 2 will have gone down, so that will have some GPE, a negative amount, right? Mass 1 will be moving. Mass 2 will be moving. And the wheel, the pulley, is going to be spinning. Pulley will be spinning, okay? So that's our equation, all right? So let's see what we can do here. So these two guys need to be equal. So my total energy final is going to be 0. And then let's plug in our numbers. Let's see, the GPE of mass 1, it's going to go up 75 centimeters, right? So we're going to get 0.8 times 9.8 times 0.75. I got to exit full screen or I'm going to run out of room. All right, plus GPE2. Well, that one's going to go down. So we've got 1.2 kilograms times 9.8 times negative 0.75 meters, right? So those are GPEs, plus the kinetic energy. So kinetic energy of object 1 is going to be 1/2 its mass times some velocity squared. Kinetic energy of object 2 is going to be 1/2 its mass times some velocity squared, plus the rotational kinetic energy of the pulley. Well, rotational kinetic energy of the pulley. Well, rotational kinetic energy is 1/2 times I. So our I is this mass. So 1/2 the mass of the pulley times its radius squared. I'm going to once again leave in R, like I did yesterday, or in the last video rather. And let's see what happens. So that's that. Times, so RKE, remember, is 1/2 I, which I've dealt with, times omega squared. Well, omega is V over R, right? Oops, pretend that's a lowercase r. So times V over R squared. And so, cool, these r's are going to just cancel out, right? Okay, so what do we get? Let's see. So this guy gives us 5.88 minus, I guess I should pick up my piece of paper where I have these numbers written down, minus 8.82 plus 0.4 v squared plus 0.6 v squared, and then half of 0.6 is 1.5, so, or sorry, 0.15 v squared, and that whole mass equals 0. So simplify it, you end up getting 2.94 equals 1.15 v squared. Solve for v, and you get pretty close to 1.6 meters a second. It's off by a scotch because of rounding, but that's basically the answer you get. All right. So it's basically just a conservation of energy problem, like we would have done before. The big trick is this, replacing the omega in that RKE equation with V over R, and very frequently you can leave R in when you calculate your I, your rotational inertia, and then the R's cancel just like they did here. Okay, so, all right, let's see, what's next? So that is that. Part B, what is the angular acceleration of the pulley? I am realizing that in my notes I found the angular velocity of the pulley, which is not what it asks for. So, pause, think for a second. All right, so probably the easiest way to do that, let me clear the screen here. Boop. Oops. So we just figured out the linear velocity. So for part A, here's what we just decided. We decided that our objects underwent a displacement of 0.75 meters. They started at rest. We figured out that the final velocity was 1.6 meters a second squared. So I think we can use this guy to calculate our linear acceleration. And if you do that, you end up getting pretty close to 1.7 meters per second squared. And so then you can use a jumper to find your angular acceleration. A over R, 7 over the radius of the wheel is 0.05. So that gives you 34 radians per second squared. Okay, so that's part B. All right, part C, the tension in the rope. So, I mean, I guess you guys already know how to do this using systems, right? We know the acceleration now of the masses. So you can just do a net force equals net force equation to find the tension. Oh, this was part B, wasn't it? There you go, part B. And I think there's value in doing it another way, just to point out that you can, in fact, do it. We have to be able to use the work kinetic energy theorem. So let's look at this. Let's find the tension in mass 1, okay? So what I'm going to do is this. I know, for part C, I know that the net work is equal to the change in kinetic energy, right? Well, my net work is my net force times my displacement, which is 0.75, right? That's got to equal my change in kinetic energy. Oh, well, that's 1/2 the mass, which was what, 0.8, times our velocity squared. That's our final, and then our initial is 0, right? So if you simplify this, you can find your net force, or better yet, your net force is really just, let's see, our net force is going to be upwards, right? Because this guy's going to go up. So you're going to have that tension minus your force of gravity, which is 0.8 times 9.8. So what's that, 8.82? No, sorry, 7.84. Cool, and solve for tension number 1. Okay, and so tension number 1 ends up being, that's got to be the smaller one, so 9.2 newtons. All right, and then you can repeat a similar process for the other rope and find out that tension number 2 is 9.72 newtons. Okay, or you can go back and do net force equals net force like we've been doing since the beginning of the year. Okay. All right, part D says use 2 different methods to find the net torque on the pulley. Boom. So here we go. Option number 1, net torque. Well, net torque is the total of the torques. So that's the torque from tension 1 plus the torque from tension 2. Well, torque is force times distance. So take the force of tension 1 times your radius plus the force of tension 2 times the radius, and then just understand that one of them's got to be negative, right? So let's make the thing rotates this way, right? So the torque from tension 1 should be our -1, I guess. So you're going to get negative 9.2 times 0.05 plus 9.72 times 0.05 meters, newtons. Whoa, my pen is backwards. That's embarrassing. And so if you do that, it gives you a net torque of 0.026 newtons. All right, so that's one way that we can go about finding the net torque. Option number 2 is to use what we learned yesterday. I keep saying yesterday, I just mean in the last video. So net torque is I times alpha. So let's see, I for disk is 1/2 the mass times the radius squarified times the angular acceleration, which we already found. Okay, and it gives you the same answer, which makes us happy. All right. Part E asks for the average power. Boom. So average power is work divided by time on the pulley. So the work done on the pulley is basically just a change in rotational kinetic energy, right? Because that's the only type of energy it changes, divided by the time. So really, we just need to find our time. So I guess I'm going to kind of cheat. So we know from before that the initial velocity of the system is 0, the final velocity of the system is 1.6 meters a second. When I found my angular acceleration, I calculated my linear acceleration to be 1.7 meters a second squared. So that's enough to find your time. It turns out to be 0.94 seconds. So that's our time. So now we just got to find our change in rotational kinetic energy. So I am going to do a thing. Remember before we talked about the work kinetic energy theorem? So in the same way that change in KE is, whoa, totally lost my train of thought. Oh, is net force times displacement. Our change in RKE should be net torque times change in theta. Okay? Yeah, because we established that up here, right? So there it is. All right. So, so this is net torque times change in theta over time. So our net torque we found before, that's 0.026 Newton meters. Oh, let's see, our change in theta, well, let's use a jumper. Our change in x was 0.75 meters divided by the radius of the pulley. My phone is ringing. They're just going to have to wait. Divided by our time. And it gives you 0.41 watts. All right. Last but not least, part F wants the instantaneous power. Well, instantaneous power is usually force times velocity. Our angular counterpart is torque times angular velocity. Well, so we already know our torque is 0.026 Newton meters. And our angular velocity at the end of the time given, well, that's just V over R. And our V was 1.6 meters a second. Our radius is 0.05 meters. Calculate that, and you get 0.83 watts. It's a really kind of boring and dull video. I apologize. Cool. There you go.